Am I audible? Yeah? Okay. Good evening to everybody over here. Thank you so much for joining our Guru Talks today. I'm Nishani Manohar, and I'm the Executive Director of the IIT Madras Alumni Association. The Alumni Association started this program called the Gurutalks, where we're trying to bridge gap between IIT Madras with the alumni and bring a lot of lectures by professors of IIT Madras to the rest of the world. But what we also do is we also have some lectures by IIT alumni who are profs globally. So today we have one special guest over here, alumnus from the batch of 1996. Professor S. Ramanathan is the inaugural holder of the Rodkin-Weintraub Chair in Engineering at Rutgers University. The group conducts research in the areas of quantum materials and devices, intersecting AI, low-power computing, and photonics. He is an alumnus of IIT Madras and received his bachelor's degree from Metallurgical Engineering in 1996. Welcome, Prof. I request you to come on the stage. We have a small token of appreciation for you. I request Sridhar Buvaragavan, the current secretary of the association, to please hand it over to him. Because he has to leave early.
Okay, thank you very much for the invitation, and thank you all for taking some time from your evening and being here. I'll try to make it worthwhile for you, hopefully in the next 30 minutes or so. Give you a snapshot of what we are doing in our group in terms of research, but I'll start with some higher level motivation for this area, why this is important, not only for the materials part of it, but also in other areas spanning computer science and electrical engineering and even other disciplines. So I'll talk about two examples. One is related to AI hardware. AI is something we are, probably are hearing many times a day, or in both in popular settings and also in your academic settings. AI is artificial intelligence. There are sort of multiple components or dimensions to AI. Of course, AI is already being used in software, in many technologies. You can see it widespread across society. But there is a lot of interest in implementing AI at the hardware level. What I mean by that is, in the electronic devices. Can you make semiconductors, work in such a way that they can help implement some of the concepts from AI into the material side of things or the device sides of things. And then I'll give you some examples of ancient intelligence, evolutionary intelligence, that also sort of fits into this broad theme of AI and robotics and so forth. So that's sort of the idea. And this is just for fun. In case you're familiar with Wordle, this is one of the examples, or one of the Wordle from a few months back. You can see there's sort of three things here I've guessed: brain, chips, and oxide. That's sort of going to be the focus of my presentation today. All right, so what is AI? First, we need to understand what is intelligence, right? And we all have different definitions of intelligence. Intelligence could be natural or artificial, as the case may be. In the context of natural intelligence, if we look at organisms that have a central nervous system, right, like us, for example, you could argue that the intelligence is a summation of phenomena that happen at multiple length scales, at multiple different scales. For example, you have molecules that form proteins and other biomaterials. They come together, and then we form our components of different organs, and then you have something called a mind, and then the mind influences behavior, right? So there is a very complex set of interactions that happen at multiple length scales, at multiple complexity levels, resulting in some manifested sets of characteristics that could fall under intelligence. Intelligence is not only part of the the things, inner workings of the central nervous system, But this is something that can also be modified, through behavior, through interactions, through our interactions with our peers, with the broader community, and based on your experience. So this is very widely studied in different animal families. So you can see animal behavior is primarily people are focused on studying survival tactics in animals, animal colonies. And there are many interesting characteristics here that contribute to the intelligence, contribute to something called learning, and subsequently how this affects the overall survival reproductive strategies, right? In AI, we are inspired by all these observations from nature, and we would like to see what aspects can be implemented in, let's say, in software and algorithms, and the focus of my presentation would be in semiconductors or in materials, and how can you see these behaviors manifested in devices, and a connection of these devices, combination of them. Eventually you build a computer or some circuit, whatever you can use it for computation, you can use it for sensing, so forth, right? And I will be talking mainly about this concept called plasticity. Plasticity is the idea of continuously modifying our thought processes, so to speak, or the connections in our brain are not static. So if you bought a computer recently, right, it has a very well set of fabricated devices, and you expect them to work very well until it reaches end of life, right? So these devices are made to operate in a way that's highly reproducible, and the human brain or animal brains are far from that. So we are continuously changing our structure of our brain, at a microscopic level, based on our experience, based on learning, based on knowledge, based on some things you may have forgotten, whatever it may be. So there is a dynamic effect that is continuously happening, and this is in part referred to as plasticity. So this does not exist in today's electronic devices. We are making devices and making them highly reproducible to work until they stop working. So this concept of applying principles of intelligence, biological intelligence, into artificial intelligence hardware must incorporate some ideas about plasticity. So I'll give you some examples on that. And from my both from my slides and also from the presentation title, there was concerns about sustainability, and this is very important. A lot of young people particularly care about climate change, care about energy use, across different sectors. Not just restricted to engineering. So in the context of AI as well, we have to be responsible, and how do you, ensure these technologies are sustainable, right? Because all of us have, probably a computer, probably one or two phones with us, so we're all using electronic devices, and they're all consuming power, right? So the question is, are there ways to reduce power consumption of these devices? Especially when the number of devices keeps exponentially increasing. That's one concern. There is also concern in terms of sustainability of AI itself, right? So if you hear, various bits and pieces of news in the media, you'll say, well, some folks say, well, AI, is going to be, could be harmful to society, could give you unexpected outcomes that were simply not planned for. So these are some concerns, and potentially valid concerns. So there is, sustainability from that perspective as well. How do you make AI sustainable? And one obvious direction is to control the intelligence of machines in terms of being able to program them the way that we want them to make them have sustainable outcomes. So these are important concerns in the context of practical applications. So in the rest of my talk, I'll go through a few examples of results from our research in terms of the semiconductor materials and devices, but I'll try to connect them to some bigger picture in the context of biological intelligence. So hopefully, even if you don't care about the specific materials we are working on, hopefully you can make some connection between what are some outstanding challenges in the field, and maybe each of you might have some different interests in this area. Maybe you will find some connection to apply them or find it interesting. So first, just a very quick, very crude, high-level background of elementary basis of intelligence in the nervous system. So we are all fortunate to have a very complex nervous system. This gives us different capabilities, what you might consider very complex capabilities compared to many other animal species. And so how does this work? Some of it is a mystery, but some of it is reasonably well understood. So there are two main components that are responsible for information processing and memory in the brain. And one of them is neurons, and the other is synapses. So neurons are wires, basically, that flow what's called action potential. So these are basically they allow electrical signals to pass through them, and they also generate these electrical signals. And synapses are wires that control the flow of information between neurons. And these are different from metal wires that are today used, everywhere. Here we use, metal wires for connecting, every time I connect my laptop to the wall, I'm using a metal wire to flow electrons, right? These wires are existing, of course, at microscopic scale in our electronic devices too. The synapses in the brain are somewhat similar, but they're also different in the sense the electrical conductivity of this wire is not fixed. It can change. It can change depending on the strength of the electrical signal it has received. It can change depending on the time interval between two signals that reach it. Okay? And the synapses can also be what's called electrical and chemical, meaning synapses can electrically connect to each other. Synapses can also spatially be separated. So imagine you have two wires, if they're not touching, if they're not making good contact, in our traditional view of flow of electricity, if you are not contacting, then there's an open circuit, right? There's no current flow. But chemical synapses are a little bit different. You can have two synapses that are spatially separated, but you have the chemical medium, where, like in our brain, for example, you have the cerebrospinal fluid. You can have chemical ejection from one synapse that diffuses through this medium to another synapse, and then you can have some sort of information transfer, right? So you can have direct wires connecting and then wires spatially separated, and you can still have information transmission. So these are very interesting characteristics of information transfer in the brain, and question is, how do you emulate some of these features in hardware, meaning in semiconductor devices or circuits. And then what you see on the right here are basically plots of synaptic weights, that is the strength of the synapses that I mentioned, these synapses wires that connect neurons, versus time. So what this means is, if you have, let's say, two signals from two neurons landing in a wire, in a synapse, depending on the time interval between these two signals, the synapse can increase its resistance or decrease its resistance or do nothing. Okay, so there is some level of intelligence automatically encoded in the synapse that tells the synapse whether two events are related or unrelated. Okay, so that's sort of the idea, and all of these sort of fall under this problem of this high-level plasticity concept. Okay, and then there is this other fascinating concept concerning memory and learning, right? So we are all, if you consider, we are intelligent. A significant aspect of our intelligence comes from our memory, right? So if you make a mistake, if you don't make it again, you say, hey, I learned from my experience, right? So, you learned from your experience, but also you were able to store that experience in your brain, so that the next time around, you recall that information and said, hey, last time I did this, that was a bad idea. I don't want to do it again, or if you decide to do it again, maybe you have a different reason for that. So no matter what, so this is, concept of memory, information storage, and the ability to recall this information. And so you could call it learning. So you learn from your previous experience, right? So this process of learning is very interesting. So this learning can happen in millisecond time scale. It can happen in minutes time scale, and it can happen over many hours and days and so forth. So this is really a multi-scale, multi-time scale phenomena. And this has been studied across many, many different animal species. So you can see here, these are birds, mouse models, and fish and so forth, where if you excite a synapse that connects two neurons with electrical signals, in millisecond timescales, the weight of the synapse will change. And so the information or the memory in the synapse has changed, and you can call it one form of learning. So in millisecond timescales, the synapse has learned something. And then this is a very famous experiment done on sea slugs. These are called aplysia. This is a very famous model system studied by neuroscientists. And so this is an example, very famous paper by Professor Eric Kandel, where they showed that when they when they shock the gill of a sea slug, it would withdraw it. So this is called the gill withdrawal reflex. And then if they continue to apply the same electrical stimulus multiple times, the response of this gill would decrease. So this is called habituation. So the animal is getting used to a signal, and it chooses to ignore it or chooses to reduce the response. Okay. So this is some sort of familiarity. You walk on the street, you see the same environment every day. You kind of don't really pay much attention because you're sort of used to many of these things. And you see something very unexpected one day, then you'll be like, hey, wait a minute. I walk by here every day. What is this new thing here? That's like a simple example of something you're familiar with. You may ignore it, and then there is this novel stimulus that suddenly attracts your attention. So we are sort of always, more or less trained to look at this, something called novelty detection, because it's a way for us to detect, let's say, danger ahead of time, something like that. So it's a defense mechanism of sorts. And then what recently people are finding is that even during sleep, our synapses are strengthening or weakening depending on what memories are being consolidated and what memories may be forgotten. So in other words, sleep is, not just you're just not quite wasting time, but sleep is, very important for us. We all know this sort of by just, people tell you all the time, hey, did you get a good night's sleep? You're going for a test or you're preparing for something important, sleep well, whatever, right? So there's this, bits and pieces of information coming your way all the time saying how important sleep is, but now people are actually studying this very carefully. And people are finding that you can have memory consolidation happening during sleep, so it's a way of learning. So if you sleep well, good chance, your brain is getting some well-needed rest, and you're also able to maybe perform your task better the next day. So there are all these multiple timescale problems concerning memory and learning in the nervous system. But this is very important, I think, because most of AI is about improving or enhancing performance using intelligence, and memory and intelligence are very closely related to each other in the neuroscience world. Right? The more memory you have, chances are you could be potentially more intelligent. Sort of a simple connection between the two. So you can then consider different tiers of intelligence. So this is a paper by a group at Baluska and Levin at Tufts University, where they look at different tiers of intelligence. So you can sort of break down the intelligence that I mentioned in the context of nervous system, and say, well, there's a genetic framework. You can have skeletal, neural networks, intelligence at the tissue, organ level, entire organism, right? And then you can have groups of organisms, like a colony, where tasks are performed very efficiently. So the very famous example is ants. Ants have extraordinary capabilities, compared to the strength of an individual ant. So a colony of ants can perform very complex tasks, far superior to what an individual ant can do. So these are ant models, are very widely studied in computer science, in sort of biology and so forth. And so you can ask questions, concerning how do you design intelligence? If you had all the resources in the world, right, and if you are tasked to build a robot, what would this robot do, right? I mean, you could fashion this robot, like your favorite, movie character, or superhero, whatever it may be, right? And you can say, well, I want this character, I want all these things, I want to fly, I want to swim, whatever, I mean, you can come up with all these different goals, but then you can say, well, but you need intelligence or capabilities to do that. And so what would those intelligent characteristics be, right? So how do you actually go about doing this? And then, how do you actually look at the minimum capability that would enable this process of learning, right? This is very important because learning is a hallmark of intelligence. So how do you actually do this? So these are some very interesting questions, multidisciplinary questions across engineering, neuroscience, physical sciences that people are thinking about. All right, so now I'll give you a few examples from our research on quantum materials, and I'll try to explain to you why this is a little bit different than what's happening today in the current, or what exists today in current technologies, current computing technologies, and what could potentially be interesting about these materials. So, if you are not familiar with band structure, you can just follow along very, I'll just give a quick superficial overview of this. So we are familiar hopefully with metals, semiconductors and insulators, right? So metals conduct electricity, semiconductors sort of poorly conduct electricity, and then insulators block the flow of electricity, right? The reason, or simple reason for this process is you have a large energy gap between states where electrons are present and then where electrons need to get to be able to allow electricity to flow. And if this energy is very large, say of the order of several electron volts at room temperature, then the material is an insulator. And then if this energy barrier is about, say, 1 electron volt, somewhere in that range, it's a semiconductor. If it's 0, it's a metal, right? A transistor, that is our workhorse of today's electronic devices. If you're working with if you ever used a computer or a cell phone, there's billions of these transistors in each of these devices, right? So how does it work? Well, you have a metal, a semiconductor adjacent to each other, separated by an insulator, right? So you have metals, insulators, and semiconductors all come together to build this one unit called a transistor. And in a transistor, you work with the semiconductor is the main component that is performing the work. The semiconductor changes its conductivity near the interface between the insulator and the semiconductor, okay? This happens by applying an electric field. And the semiconductor stays a semiconductor throughout the entire function, throughout the entire operation of your device. In quantum materials, or at least some classes of quantum materials, you can have something called a metal to insulator transition. So you can start with a metal conducting system, electron conducting material, and then you can change the nature of electron conduction in this material to make it less conducting or very poorly conducting. So you have one material that you can do something to it, either apply some external stimulus, external stress, whatever it may be, and change its conductivity drastically and make it into an insulator. And this process is reversible. So when you apply, let's say, a stress, mechanical stress, you make an insulator, and then you remove this stress, the material could go back to its original state. So you have a process to reversibly change the conductivity of a material, okay? So that makes it very interesting. So I'll give you a couple of examples of materials that show this property and how we can use this to build some very simple proof of concept electronic devices for computers. So this is one example, VO2, vanadium oxide. It's a very famous material that undergoes a metal to insulator transition around 67 C. So it's close enough to room temperature, not quite room temperature, but above room temperature, close enough. So you can see here the resistance is low, let's say high resistance, and then at some critical temperature, it drops its resistance. So you have this switch. It's basically a switch, right? You have high resistance, low resistance, and there's a sharp drop. Electrically, you can basically see here, you have a current, and then you have a sudden jump in the current at a critical voltage, and you see this is a phase transition. So this is a metal to insulator transition where you see this abrupt jump in the current flow. So this is a switch. And switches are the workhorse for electronic devices. The transistor is a switch, right? But this is a different kind of switch because you're changing the nature of the material itself from insulating to conducting. So what can you do with this? Well, you can do many things with this, but one example in the context of my previous few slides are we can build an artificial neuron with this. So you can see here, this is a neuron signal from mouse brain. So you can see these abrupt, sharp jumps in voltage spikes. So these are corresponding to voltage signals coming propagating in a mouse brain slice. And we can mimic the same process or something very similar using this example I just showed you, this VO2 metal insulator transition. And you can see these sharp jumps in current that flow through this material as we go from an insulator to a conducting state. So when it's insulating, you have less current. You apply some critical stimulus, it becomes metallic, and then you increase the current flow. Remove the stimulus, it goes back to being insulating, so you have less current flow, so you can sort of keep going back and forth, right? So if you connect a switch like this to a capacitor, as a capacitor charges and discharges, you can have these oscillations. So these type of oscillations are the basis for information transfer, signaling in the brain, and now we have a artificial material, a synthetic material that emulates this characteristic. And you can do many things with this. You can build computer circuits with this. You can also study problems in neuroscience if you're interested. You know, you can sort of try to bridge the gap along different research fields. So this is a simple example from our work a few years back with some collaborators at University of Chicago. So you can see this is what's called the knee-jerk reaction. So if you've ever been to a doctor, you'll see they might gently tap your knee with a hammer, right, to just check if you're able to sense that signal, right? If you feel nothing, then maybe it's a problem because your nerves are not working right or something like that, right? So what they are really looking for is this, you are moving your leg, when you're being struck with the hammer, and this is called the knee-jerk reaction. So it's one of the very simple neural circuits in our body. You basically have two neurons connected through a synapse. So it's there's in our spinal cord, in our nervous system, we have billions of neurons. So it's really very complicated, stuff, right? But if you have just two or three of them in a circuit, then it's very simple to start thinking about, okay, how can we understand that? So that's why this is a very famous circuit. So you can sort of emulate this process in a synthetic device, in a semiconductor. So this is one artificial neuron, this is another artificial neuron connected by a wire, right? So it's a resistor. By changing the weight of this resistor, meaning you can imagine this to be an artificial synapse, you can have signals that propagate through one neuron, go to the other neuron, or signals from one neuron do not propagate to another neuron. So in this case, this would be a less than optimal device because you're not able to transfer signals, so that's a problem potentially in the biological context. But in the synthetic context, you can control different parameters of your circuit and look at how the electrical signal is being transmitted. So these are just a very simple example of how you can use a synthetic device to understand some circuit level behavior, right? So you can go from material to device to circuit, very similar to what I mentioned early on, molecules to neurons and synapses to decisions that we make or behavior, whatever it may be. So that's sort of the way of thinking about it. Now I'll give you one more example, and this is maybe a bit too technical, but we'll see. I talked about transistors. In transistors, we have this insulator like hafnium oxide, silicon dioxide, that sustain electric fields. And what we have shown recently is we can introduce similar types of dielectric interfaces at the semiconductor boundaries, and we can introduce electronic phase transitions. So you see here, this is a conducting AFM image, meaning a atomic force microscope image of current flow through a material. So this is finite current flow through the material, and when we add dopants, especially in this case hydrogen, we can actually suppress the electrical flow in this system. So this is an insulator, so you can see no current is flowing. So we can go from a conducting system to an insulating system by adding electrons or adding hydrogen, which donates an electron. So this is a very interesting physics here. if you're familiar with, say, electrical conduction, the more electrons you add to a material, the more electrical conductivity should increase. And here it's the opposite. So when we have a conducting system, we add electrons to specific orbitals, electron orbitals in the system, you can actually suppress the flow of electricity. So this is interesting physics, but also this can be used to build many different types of artificial neural networks. And the way we can do that is by controlling the amount of current flow through the material. So this is a starting system, and if we add more and more electrons, depending on how many dopants we add, we can systematically change the conductivity. And you can see here, so these are all optical micrographs. So this is a conducting starting system. So because it's a conductor, it's opaque, it's not transmitting light. And then as we make it more and more insulating, it becomes like glass, so you can actually see through it, right? So you can go from a opaque to a transmissive system. So it's basically a window with tunable transmissivity. So these are ways we can control effectively the weight of a synapse, the electrical resistance, and you can use this to build different types of artificial neural networks. So I'll show you one last example and then I will stop, which is evolutionary intelligence. I mentioned this at the beginning of my talk, and this may be also fun to share with others. If they ask you, hey, what did you do today evening? You can say, I learned a little bit about sharks today. This is fun. Sharks are, apex predators in the ocean, right? So very, very daunting creatures. They have a very interesting class of sensors called ampullae of Lorenzini. These are basically sensors distributed around the mouths of sharks. And this was first noted in a book by this biologist, Lorenzini, almost over 300 years back. And this interface, this sensory intelligence capability, allows sharks to detect prey even before they see them. So even before they come in contact, they can actually sense the electric fields from that prey because the water is, especially the ocean water is conducting. So you can actually have ionic currents that flow through the water, and the sharks can sense them. So you can basically have the shark that is angling towards a predator, and then when until it can see it, and then it can sort of go and target it. So there's a very famous type of intelligence, sensory intelligence, and if you look at the people in evolutionary biology, they have studied this, and said, okay, this was originally observed in animals that evolved almost more than 400 million years back. And some of these animals are actually, and since then, many animals also lost this intelligence. So this class of sensory intelligence is only there now in a few classes of like sharks and stingrays and like a few other species. And so we wanted to emulate this, and this will be my last slide, which is we can basically take the same material I mentioned before, this phase transition material. We can add hydrogen to this system from water. Water has protons, so we can add protons to this material, and we can change the conductivity of this. So it's essentially when you change conductivity of something you're acting, it can function as a sensor. And this mechanism of sensing of hydrogen or proton incorporation into the material is very similar to how sharks sense their prey. When you have bioelectric fields of fish approaching a shark, protons can go from the water into the shark's ampullae, and then they can sense that there's some species coming towards it, and then you have sharks typically have a few thousand of these sensors distributed around their mouth, and so depending on the strength of the signal that's coming, it can basically sort of triangulate the signal, and so it can go towards the stronger stimulus. So it's sort of interesting. So we sort of wanted to look at this and see if we can emulate it, and this, fortunately we were able to show that this actually concept works, and so we were able to go from materials all the way to this idea of evolutionary intelligence, sort of revisiting ancient forms of intelligence that have been lost. So it's sort of simple analogies. If you have some famous recipe in your family, and you say, hey, this is my this particular dish was, has been passed down generations. My great grandmother made it, and now we are learning from them, right? So there's this sort of trace of intelligence or knowledge that keeps getting passed down, and then many of it is lost, and some of it you can retain, or maybe a small part of it you can retain. And sometimes you might wonder, hey, what if I knew more about my ancestors, right? So it's the same idea here. There's lots of intelligence that evolved when complex life evolved, and not all of it has been sort of kept. Some of it has been kept, a lot of it has been lost. And there's this field of evolutionary biology where people try to think about this and say, what are some aspects of intelligence that would be beneficial to have today or in future technologies, right? So there's sort of very interesting cross-disciplinary interactions all the way from biology to engineering to computer science, right? So there's sort of a very interesting, fascinating field. And so I'll stop here. This is my last slide. If you have any questions, I'm happy to take them. But I just want to sort of leave you with this idea that interesting physics, interesting quantum materials could form the building block of future computers, and AI is something we are all somewhat familiar with, or we hear about it. And what I want to leave you with is one path towards sustainable AI is reducing the power consumption of these devices, of our computers and cell phones and whatnot. And hardware could play a very important role in that. So thank you very much for your attention. I'm happy to take any questions.
Yeah, I'm curious about the stability and the degradation of the quantum materials that you're manufacturing, how stable they are, because generally the quantum materials are tend to be unstable. So that is one question. And how do you manufacture? What's the process that you use for manufacturing these materials? Is it sort of scalable, or what stage of like the technology to commercial scale? Where is it? I'm just curious.
That's a great question. I mean, so we make these materials by what's called thin film deposition techniques. So we use techniques like physical vapor deposition or chemical vapor deposition. So to make a good semiconductor device, you got to make the material, and then you got to make contacts, electrical contacts, and so forth. So the material has to be very stable during all that processing, and then it has to be stable during operation as well. And there are fairly standard metrics for showing stability of these types of devices. So they have to be, you have to show stable cycling of the electrical states. They have to be stable in air, for example, during all the processing. They have to operate over some temperature range. So there are these standard metrics. So we show the performance under those types of conditions. So that's important. That's a very, scientifically, there are many avenues to pursue. But when you want to say, well, hey, I want to build a practical device with this, then you got to address this question of stability. Yes. Yeah.
Hello, sir. Am I audible? Yeah. So wonderful talk. But I would like to know more about these models. We train it on biological intelligence. So basically we try to mimic biological intelligence. But when it comes to human, if animals we are going to mimic to train our data set or to train the model, then we won't see any biasedness. But when it comes from human, then we will definitely see some biasedness there in the model. It will be reflected in the model. Because we are biased, so we try to manipulate data. It's not like everybody, what makes sense to us, we actually try to follow it. So how to avoid that kind of biasedness in using artificial intelligence? So it should not be reflected in data set which is trained on these biases.
Yeah, I think, that's a great question, but I think that's more for people who develop algorithms for, say, recognition or certain types of, decisions for outcomes. We are more interested on the hardware side of things, and that's why, I mentioned this at the beginning. One of the aspects of sustainability is power, but the other concerns the intelligence itself, right? And I think what you're asking is, more related, let's say, towards ethics or equity or things like that, which is very important. I think one way to do that, this is my understanding, I may be limited in my answer to this, is controlling the memory of the AI system. Because memory is directly related to intelligence. So the more complex ways we can manipulate the memory, I think you have a better chance at controlling outcomes, say, through, that are influenced by unwanted or undesirable bias. So for us, the way we try to address this issue is by offering materials or devices where we can control the memory very, very, very exquisitely by all these doping or by controlling the electronic structure and so forth. But I think today, the bulk of this problem that you identified or pointed out, I think is addressed through algorithms. So more like, say, in computer science or applied math, somewhere in that range, where how does a system make decisions? I think so. That's where it's done today, I think. Yeah.
Thank you, sir.
Thank you. Good question.
Thank you, Professor Ramanathan. So it was a wonderful session. I have a question. So we are talking about this neuron getting replaced by these materials, right? In the sense, this material will act like the way in a human brain the neuron works. So it's very similar to talking about a perceptron, right? In a artificial intelligence world. So the activation functions and other things which we talk in a perceptron world, is that what we are trying to mimic over here? And can we write mathematical functions which can give us that jump and a switch kind of thing in these material, and how to program that particular thing?
Yeah. So yes, we can build artificial neurons with exactly what you just mentioned, this idea of a sharp switch. And not only that, you can control the threshold values that you need to activate this off to on. Or for example, if you need to accumulate certain charge, then you can go from off to on. So I showed you one slide, and I kind of maybe went a little bit fast, but if you recall this chart, you see you have biological neuron, and you have these action potentials, and we have these sort of equivalent of that. You have these current spikes. So I think what you're asking is related to how do you control this, right? So you can control this by controlling the chemistry of the material that we start with by doping or the structure. We can also control it by the amount of electrical energy that we provide to it. And the beauty is you don't need to provide this electrical energy continuously. You can provide a little bit of electrical energy and then stop it. And then as the system is relaxing back, you apply a little bit more electrical energy, and then you can sort of push it, you can prime it towards this step function, this switching. So that gives you control in context of energy efficiency. You don't need to continuously supply electrical power. You supply some power, then you go back to zero, then you go back. So this activation function onset can be experimentally controlled, which is very important actually, because especially in a circuit, you want some neurons to fire and some you don't want them to fire. So you should have multiple ways to control the activation of the circuit.
Any real-time use cases have been proposed for this, or you tried it in a real-life scenario someplace?
Yes, absolutely. I mean, we have shown some examples, and there are many other groups worldwide that are working on this. The use cases are typically recognition accuracy, pattern recognition accuracy, how much energy it takes to recognize certain patterns. Can you do it more efficiently than, say, in software? And then solving computational optimization problems. So these are all sort of examples where these types of devices and circuits have been shown to date as very powerful engines that can do mathematical operations. Yeah.
Thank you so much.
Thank you.
I have a question. I want to draw a parallel of meditation with AI. Okay. So I've been in an organization where they meditate, and they say with the proof that the neural connections get thickened when you meditate. It goes to different alpha, beta, gamma states, and that helps with human efficiencies and all that, right? So, and when you mentioned neural paths here, I was just curious, can AI be looked into for accelerating, right? Because meditation is finally is a catalyst there. Similarly, is there anything here in AI
I
too?
think that's a fascinating question. You know, I mean, I mentioned this earlier, right? This idea, you know, I mentioned sleep, and you're talking about meditation, and it's sort of, it's not the same, but there is some sort of connection between the two, right? You're in a state of calm, hopefully a state of peace, and it turns out that, you know, contrary to what you might say, hey, why are you just sleeping? You know, sleeping is actually very important. You know, you want to have, you know, good enough sleep because your synapses are, like you said, thickening, or, you know, your memory is being consolidated, and I think that's helpful for the next days or immediate future tasks. So I think in the context of what you mentioned, like meditation, it's sort of similar idea. You know, how do you control the activity of your brain, right? And you don't want to go into overload because you're first of all consuming energy, but also, you know, you might sort of push yourself beyond a certain, you know, criticality. So I think there are all these ideas in terms of controlling the synaptic weight, that is the strength of the synapses. And I think AI hardware might give you more degree of freedom to control it, because, you know, when you are, say, sleeping or something, we are trying to put ourselves in that calm state, but you're maybe not quite able to connect, microscopically, maybe not at an individual synapse you are able to control. It's maybe overall, you know, you're saying, okay, I feel better now. But with these type of circuits, you can go to each wire, for example, and control the strength of these wires, because externally we can manipulate them. So I think that gives you maybe a better degree of control, a finer control in the context of strengthening and weakening synapses. So I think that's definitely, I'm sure this will become a very important area as we go forward. Yeah, it's a great question. Yeah, thank you.
Hi,
Yes.
sir. Hi, sir. Hi, sir.
Oh, yes.
I have one small question. As a metallurgist, this plasticity of materials, is it helpful for artificial intelligence?
Yeah, I think, so I mentioned plasticity in the context of electronic plasticity. By that I mean manipulating the electrical properties. I think maybe in metallurgy you might mean mechanical plasticity, right? Elastic plastic deformation. So the context of, in that context, if you are mechanically transferring information, that is, if the mechanical properties of the material can help in control of information transfer, then plasticity in the mechanical sense will be absolutely very important. So let's say the stiffness of a material is directly responsible for how electrically conductive it is, let's say. And so if you can control the plasticity, or if you can control, say, the dislocation density in the material, something like that, so therefore you're affecting the electrical conductivity, then it is going to be very important. So understanding mechanical plasticity can have direct impact to AI if your mechanical plasticity is the basis for either transmitting information or storing information.
Why I asked is they are making some body parts, knees and all. So with these sort of materials, so this artificial intelligence, when it coupled with that idea, will it improve the technology?
Yes. So if you are making, say, prosthetics to implant into the body, and so of course there is the biocompatibility part of it, but if you can engineer your mechanical properties such that it helps the artificial neurons to grow, the biological neurons to grow better, or if they can accommodate the deformation that the neurons can branch out, you are going to help recover function better. So in that context, it will be very helpful. Yes.
Thank you, sir.
Thank you.
I'm curious about if there are any similar parallels for energy storage and conversion, like electrolyzer or battery applications. Like the way you did for semiconductors. Are there any interesting parallels?
Absolutely. I kind of did not talk about that at all, but that's a great observation. And the reason that is there is a very strong analogy between the two is because we are, in a lot of the AI hardware, we are, in addition to moving electrons, we move ions. Like we can move protons, for example. We can move sodium ions. And it's not surprising, hydrogen is used in fuel cells or electrolyzers. Sodium is used in batteries, right? You can do the same thing with lithium, right? These ions, lithium and sodium, move slower than hydrogen, for example. Certainly, they move slower than than electrons. So there is a speed bottleneck. But in terms of proof of principle, if you want to make the connection, the analogy between a battery and these type of information devices, you can do that very nicely because you can move electrons and ions, very similar to what happens in a battery. So the equivalent of charge storage in a battery would be equivalent of, say, memory strengthening or weakening in some synapses. So yeah, that's a great observation, yes.
Actually, as you said, sustainable AI with quantum, I'm hearing first time. So I'm just curious to know, because when you're saying sustainable or this one, right? So I'm just curious to know that with this approach, will we be able to beat the Moore's law so that actually you can also have a better footprint of your devices?
Yes, yes. So that's a great question, and yes, answer is I think yes. And one very simple analogy I'll give you is to build, let's say, an artificial neuron with silicon technologies. You need roughly anywhere between 6 to 25 transistors, somewhere in that range. And with these type of devices, you can have a single device that can show these oscillations and help reduce the footprint by a factor of 10 or so. So that already is a significant benefit. Secondly, the operating voltages of these devices can be scaled well below 1 volt, whereas silicon technologies is challenging to reduce the operating voltage below a certain value. So already there, just in these two characteristics, you have two, I think, very compelling reasons how you can make them more energy efficient. So I think, I think that's a great thing. And the fact that the properties are observable at room temperature means you don't have to cool these to very low temperatures, right? So cooling is often a huge problem because it consumes a lot of energy to cool something below room temperature. So the fact that you can have quantum phenomena at room temperature is really fantastic. So you can reap these benefits without the additional barrier of going to low temperatures. Okay, well, thank you very much for your time, and I appreciate all the questions. Appreciate it. Thank you.
Thank you for such a wonderful session. Get to know a lot of things by listening to your talk, and I think IIT Madras is also going towards the interdisciplinary way, and your talk was just the perfect example for that. Thank you to the audience. Thank you, everybody. We do have some snacks boxes. Please do take them with you on your way out. Thank you so much. Thanks. La, 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 la.